S.S.Takalkar, of course, yours Hindi teacher. Dear friends, our point second law of thermodynamics, entropy and Gibbs energy. Here we have seen the limitations of the first law, and all these limitations are overcome by the second law of the thermodynamics. Those are the objectives of the second law. Let us highlight some of these objectives of the second law. Here, objectives. First, it gives, second law gives the direction of heat flow. Right? Secondly, it also gives the conditions for spontaneity of the process of the reaction. Also, it also gives the maximum fraction of heat that convert into work. Right? And as you know, different statements of the second law made by Planck, okay, by Clausius, by Carnot. You studied it last time, etc. Now we are going to study very important statements of the second law based on entropy concept. As we consider the second law, it like to say that the Q or heat of the system cannot be converted into the work. However, the work can be converted into the heat. Any condition. But for all the conditions, heat cannot be converted into the work. Particular conditions are required. Again, all the 100% efficiency is also not possible. That means all the heat not converted into the work. Okay. Now, this law is considered significantly the conditions for spontaneity of reactions. Spontaneous reactions means which are taking place in its own accord without any intermediate once it is started. Right? Generally, naturally occurring all the processes are the spontaneous one. That means all the naturally occurring processes tends to completion, tends to attain the equilibrium. Okay. So here, what happens when any naturally occurring process is taking place? There is in naturally occurring, or one can say the spontaneous processes. Okay. There is increase of randomness. That is disorder. Okay, disorder. Randomness, that means disorder. And the entropy, that is the new function we are going to study. As like enthalpy, entropy, this is a new one. It is the measure of the disorder or randomness of the system. Actually, absolute value is not determined, but delta S is calculated, and the entropy change of the system, if we consider one of the example, suppose S2O solid, that is ice, is converted or in equilibrium, it is further it is in equilibrium with S2O in a gaseous state. Yes. Okay. So this is a equilibrium between the solid and liquid that is taking place at the 0 degree Celsius, 0 degree Celsius, right? Equilibrium temperature, and the amount of heat, that is the enthalpy change of this fusion, is 6.01 kilojoules per mole. Here, this is the vaporization, and enthalpy of vaporization for the water is 44 kilojoules per mole. What it indicates? At low temperature, so here if you consider solid state of any material where the particles, it may be atoms, ions or molecules, they are arranged well orderly. When it turns into the liquid, the randomness increases. The outer molecules in water state, liquid state, they are random. Okay. So here, suppose this is the entropy of solid, the entropy of liquid, then delta S, that is the entropy change, is S2 minus S1, and in this case it is increases. Here increases. Okay. Or it is positive. It is positive. So here S2 is greater than S1. Okay. Yeah. Now this is the liquid state. Further, if you heat and these molecules which are already in random, they get separated like this. They are separated like this. Okay. So here, suppose S3. Again, this S delta S is positive, but this is slightly, okay, slightly more than this one. So entropy increases, but delta S is high. Is high. Or we can say like this. Yeah, then change in entropy. So here the entropy change, that is the disorderness, right? Randomness of the system is more at the lower temperature than at the higher temperature. So here one can write here delta S is inversely proportional to the temperature, absolute temperature. Okay. Or delta S can be given the whatever it absorbs reversibly at absolute temperature. So here it is at 0 degree Celsius, but remember always in thermodynamics the temperature is always considered in Kelvin, not in degree Celsius. So here it is 273. So here delta fusion entropy is, one can write here 6.01 kilojoules per mole, and this temperature 0 degree, that is 273 Kelvin. So here the kilojoules per, this is the Kelvin. Kilojoules per mole per degree, kilojoules per mole. Okay, per degree Kelvin. Okay, for example, whereas if you consider this process, what happens here? The vaporization entropy is equal to this delta H, vaporization accounting, is equal to 44 kilojoules per mole divided by 373 Kelvin. Or one can write for the entropy here delta S, entropy change of the system, can be defined the heat absorbed by the system reversibly at the given temperature. Okay, this can be for example, QP at constant pressure, if the process carried out at constant pressure, then this can be written as Fx enthalpy of fusion T, or this can be also written as the vaporization. So here this is the different applications entropy of T. Okay, and this can be very clear with the help of this. So here already discussed, these are the equilibrium states at the paper. They are also equilibrium states. So here one can find here a very small heat, 6.01 kilojoules per mole is absorbed, and randomness increase is very high. So at lower temperature, randomness occurs to be high than the randomness which is occurs in this state, where it is absorbed very high heat, and the randomness is found to be comparatively very low. Okay, so this is nothing but the entropy change for any processes. Now one can consider here this entropies. What is the spontaneity? Spontaneity. Now, as you learn in nature, every processes, every activities, they are tends to increase the randomness, increase the order state. For example, if some people are in a queue, but it is not remains long times, they are going to disturb the queue. Similarly, any naturally occurring processes, the particles or atoms, molecules, whatever are there, they are tends to increase their entropy. That means there is an increase of the randomness. So here, what is the relation between, or how the second law can be expressed or state in terms of the entropy? So one can consider here second law. We are going to study statements of the second law based on the entropy. Okay. So yet you are come to know that is the entropy, that is the measure of the disorder. More is the disorder, more will be the randomness, and naturally occurring processes tends to the equilibrium with increasing the randomness. Okay. Then friends, the second law can be stated in terms of the entropy, that is statement of the second law based on entropy. It states that is naturally occurring, or if you know, naturally occurring processes tends to increase the randomness, there is an increase of the disorder. So in the universe, what happens? The total entropy of the universe always increases. So here one can state that the entropy of the universe is increases. So what is the entropy of universe? That means one can write here delta S total or universe is equal to delta S of system plus delta S of surrounding. Okay, surroundings. Practically, it is not possible to determine the entropy change of the surroundings. So here one can convert the entropy of surrounding in terms of practical observation. So how? So this is the one of the statement of the second one. What is that? That is the entropy change of the universe is going to increase. That means it is positive. Okay. Or get to that. Okay. In short. Okay. Or if you consider any naturally occurring, okay, naturally occurring or occurring processes, or what is called as the spontaneous processes. Okay. In spontaneous processes, it tends to any tends to occur to attain an equilibrium. So naturally occurring or the spontaneous processes, right, tends to attain the equilibrium. So it means at equilibrium the both states have same entropy change or zero entropy change in zero. Entropy change when the two states, right, initial and final states are at equilibrium, that means they have same entropies. So here the processes at or reaction at equilibrium delta S is 0. Okay. Or before the equilibrium, the processes going to attain the equilibrium, that means it taking place in its own accord. It has a tendency to taking place undergoing that reaction, that is, it is spontaneous. So here in a spontaneous reaction, that is for spontaneous reaction, delta S is greater than 0, or for non-spontaneous reaction, delta S is less than 0. Okay, this is very important things. Conclusion. So here the spontaneity of the reactions can be decided according to this. Delta S, if it is 0, the process is said to be at equilibrium. If it is positive, that means increases entropy, that is a spontaneous process. And if the delta S value is negative, less than 0, it is a non-spontaneous reaction. But this is not at all. Practically, it is found that this criteria to decide the spontaneity of reaction is not correct for all the times. For example, consider okay. So here one can say that the criteria for spontaneous reaction, delta S is greater than 0, and or for non-spontaneous, delta S is less than 0, negative, and equilibrium, delta S is set to be 0. Okay. Now the question is that does these conditions are sufficient for all the reactions to decide the spontaneity of that process, of that reaction? It is said to be, it is not at all, because some reactions having a positive delta S but they are non-spontaneous, some has negative, still they have spontaneous. For example, if you consider hydrogen peroxide when decomposed into H2O plus oxygen, the delta S entropy change is found to be 63 kilojoules per mole. Okay. And if you consider also some of the hydrogen plus oxygen giving H2O, the delta S found to be 163 kilojoules per mole. In this case. Okay. So what it means? Both are spontaneous reactions. That means, what is the conclusion? That means delta S is cannot decides spontaneity of a Okay. It cannot be decided spontaneity of the reaction. So here, then how the spontaneity can be decided for the reaction? Therefore, as you know, in this law, second law, the entropy of the universe increases, and universe, that means system as well as surrounding. Practically, it is not possible to determine or to measure the entropy of the surroundings because it is not under our observation. We only study the system. So does it possible to convert in terms of the system all the thermodynamic state functions. Okay. So here this can be considered. Therefore, to overcome these things, a new function is determined or suggest, and that is known as the Gibbs free energy. Invented by American great scientist. Gibbs is suggest a new thermodynamic or state function denoted by letter G, and by the definition of the Gibbs free energy, or simply sometimes said as the Gibbs energy. Okay. So here G can be defined as H minus Ts, as all are state function. Gibbs function or this enthalpy, temperature, entropy. All these are the state functions. Therefore, delta G also state function. So if you consider G1 is equal to H1 minus T S1 at constant temperature. So here, therefore, delta G can be written as delta H minus T delta S at constant temperature. Okay. So the free energy change, that is Gibbs energy change of the system is equal to the enthalpy of the system minus the absolute temperature and the entropy change of that system, of that process. Okay. So here, if you consider, this is the equation. Again, consider now the next point. Then, if you consider the free energy by the definition H minus Ts, H means the total heat content of the system, right? Minus this factor. So whatever temperature and whatever are the entropies, right? That is the disorder. Some energy is required to make the system random, to make the system disorder. So some of the energy, heat energy, is utilized or wasted to disorder the system, and it depends upon given temperature also. As you know, as per discussed here, lower the temperature, higher will be the disorder. Higher the temperature, lower will be the change in the disorder. Okay. So here, this factor is subtracted from the actual enthalpy change of the reaction, that is total heat contents of that reaction. Okay. So the remaining part of the energy is nothing but the Gibbs free energy. So one can consider it is nothing but the useful energy, right? Useful energy. Okay. Then, if you consider we are going to relate delta S total, right, of the system. This is of the system, and this is for the system, all the system. But as per second law, the total entropy change, okay, total is given. Of course, the inverse total, or one can write the total or inverse is equal to delta S of the system plus change of the entropy of the surroundings. Okay. enthalpy change of the process at equilibrium at given temperature T. It may be a fusion reaction, it may be a vaporization reaction, or it may be any phase change, sublimation, condensation, freezing, whatever. So here, as you know also, as you know, but delta S is equal to delta S, because in fact actually Q reversible upon, but this is nothing but the QP reversible. This is equal to delta H upon T. Okay. Then delta S of 16 is equal to, what is that? The delta H upon T for the 16. Okay, this is plus, then minus delta H of the surrounding. Okay. Or one can say delta S of the surrounding is equal to minus delta H of 16. Okay, so we are going to use this formula. Okay, then consider. So we require this. The entropy change of the surrounding is nothing but this minus this. Okay, because if the entropy of the system increases, it means the entropy of the surrounding decreases. Sorry, this enthalpy. The enthalpy change of the reaction increases, same time the enthalpy change of the surrounding decreases, or vice versa. The enthalpy change of the system decreases, that means the enthalpy change of the surrounding increases. So the minus sign is given there. Consider. So we can write this formula here again. Delta G is equal to delta H minus T delta S. Okay. Now, one can substitute here, there, here, delta S, consider, S dot delta S total, therefore, delta S total is equal to delta S of 60, okay, this is for 60, plus delta S of the surrounding, here, surrounding, it is this, okay, minus delta H upon T. Right, this is also 60. This is for the total. Okay, so one can possible, we have converted it by this way. So simplify this one, then this T, this can be written as T delta S minus delta H on T equal to delta S total, or one can get T delta S T. This T. This is the temperature. This is the total. Okay, total is equal to T delta S minus delta S. Multiply to both sides by minus 1, or here the minus 1. Okay, here multiplied by minus 1, it becomes here now plus. So here this means the minus times T delta S total is equal to here delta H minus T delta S. Now if we compare these two equations, this is equation and this equation derived by the given by the gives, and one can obtain this. So as the left hand sides are same, therefore the right hand sides are also same, therefore left hand sides are also same. So here this means, what it means, okay, therefore that is delta G equal to minus P times delta S. Okay, whatever it is. So what it indicates, it suggests that is first, that is delta G and delta S. Okay, delta G and delta S has given system, if this is positive, it will be negative, or if it is a positive, it will be negative. Okay. Second, here, if you consider at equilibrium, if you consider this element, okay, this element, at equilibrium, what is happened here? At equilibrium by second law statement. What is that? That is second law. One of the statement you study that for the spontaneous processes, what happens? Entropy increases and until the equilibrium reach. That means delta G is greater than 0. It is a spontaneous reaction equal to 0. It is at equilibrium or spontaneous reaction. And it is less than 0, that is a non-spontaneous reaction. Okay, now you consider delta G value at 0 for this definition. Then 0 is equal to delta H minus T delta S, or T is equal to delta H upon this delta H upon this delta S. So this is the temperature where the spontaneity of the reaction changes. Above this temperature, some reactions are spontaneous. Then below this reaction, that reaction is non-spontaneous. Or any reaction at this temperature, below this temperature it is spontaneous. Then above this temperature it becomes a non-spontaneous. So this is the temperature which is the boundary of spontaneity of that reaction, right? So this is the temperature at equilibrium. Okay, where delta H and delta S. So from this, what happens? What it gives? It gives the values of delta H and delta S are independent of temperature. Okay. Ratio to this. Then also we are going to study here very important point. If now if both are positive, if both means delta H and delta S, both means that is delta H and delta S are either positive or negative, then spontaneity of reaction determines or depends upon temperature. Very important chapter. If both are positive, that means in this equation, if delta H value is positive, also delta S value is positive, then this positive minus this is positive. So this positive minus this positive. Okay. So here the one can think that the whatever is the delta G value obtained is depends upon the temperature. If the T is high, then the delta G will be low. So we are going to study how the spontaneity depends upon this temperature for this condition, right? However, if one is positive, one is negative, or one is negative, one is positive, then it not depends the temperature. So the spontaneity of the reactions may or may not be depends upon the temperature, and spontaneity of the reaction always be determined not by the delta S but according to the delta G values. So these free energy changes, these are very important. We are going to study here. Now, consider. So here, as per discuss here, one more thing to be obtained, that is delta G is equal to the negative indicates reaction is spontaneous. Delta G is equal to 0. Reaction is at equilibrium. And if delta G is equal to positive indicates the reaction is non-spontaneous. Okay. Consider here delta G for spontaneous reaction, delta S is positive. Okay, that is greater than 0, positive. But here it will be. But this is not the criteria, and this is only the for determining the spontaneity of reaction, delta G only. How? Consider this table, delta H value, delta S values, and spontaneity of reaction using delta G delta H minus. Now let's first discuss if this is a negative, this is also negative, or positive, or this is positive, this is negative, those are negative, or those are positive. So here, if you consider delta H, delta G is equal to delta H is negative, so this is negative, and minus T, delta H is positive. So whatever value it becomes negative, total becomes a negative. That means the reaction is the spontaneous at all temperature, any temperature. Okay. Now consider the second criteria plus. Okay. Now what is unique to delta G? This is positive. Delta S will be positive minus T times delta G. Delta S now. What is it? Negative. So negative into negative. Okay, it becomes positive plus positive. That means total equilibrium positive. So delta G is equal to positive means that is reactions is non-spontaneous at all temperature. Okay. Now consider one more type, that is if it is a negative and both are negative. Then delta G is equal to. So this is the delta S is negative minus T, and delta S is also negative. Then what happens? This is a negative value. This minus into minus, this is a positive value. Okay. Into multiplied by some positive. Okay. So here negative and positive values. Okay. Positive. Then what is the value of this temperature? If it is more than this value, then total G will be positive. If it is less than this value, then it is a negative. Okay, so one can consider if temperature is high, high temperature, high or low. What is the minimum lower temperature? Of course, the 0 Kelvin. Okay, if it is 0, then what is it? It will be a negative. And what is the higher value of T? No limit. So here, whatever it be, it is high, then whatever value this becomes a positive. Delta G is equal to positive. Okay. So this means the delta G is positive, that is a non-spontaneous reaction at of course higher temperature, or this is a spontaneous at lower temperature. Now the fourth and the last one, conditions of the temperature consider. Okay. Now with delta H, delta S, delta G is equal to delta H minus T delta S. If both are positive. Now in this already discussed here, if the both values of delta H and delta S are either positive or negative, then the spontaneity depends upon the temperature. So here delta G is equal to, if delta H is positive minus T, this is again a positive value. So this positive minus this. So again here it depends upon the temperature. If the temperature is high or temperature is low. Now the low temperature means the maximum capacity, that is the 0 degree Kelvin, that is 0. If you consider low temperature, this is 0, so it only a delta G is equal to 1. At higher temperature, so having no limit, so this negative value is obtained, delta G is equal to negative, and it means the reaction is of course spontaneous, means at high temperature if the delta H and delta S both are positive, then at high temperature only it is spontaneous, otherwise it is non spontaneous. Reaction at low temperature. Okay. So yet you come to know the spontaneity can be determined on the basis of delta G values and not on the delta S or delta H values. Dear friends, with this we are going to study the next topic, that is the third law of thermodynamics, but not now. It will be, we are going to study during the next lecture. Still, you give subscribes my these lectures.